do you want to start us off here, or do you want me to? Do you want to do this?
We were going to let Daryl do that, remember?
Okay.
Mr. Wiley? Mr. Wiley, are you available?
You're on mute.
There we go. So, am I introducing? Okay, well, thank you everyone for tuning in and to our training today. Mr. President, were you wanting me to go right into the officer information about our officers for next year? Is that what you were wanting me to do?
We want to start off with letting everybody know, that we are the SoCal Iaei, and that our elections are coming up in November, and we have a slate at this time with some openings on it, and we are looking for those that are willing and available to fill those positions. And then also we wanted to give everybody a reminder of our next meeting. Go ahead, Daryl.
So as our president, John Bayless, has just mentioned, welcome to you all to our SoCal chapter Iaei training seminar today. And what we do want to let you know is, as part of our chapter, we have a position that is open for the next cycle. Now, without digress for a quick moment, if you're not speaking, if you could please mute yourself, and then chime in when you've got unmute when you've got when you're wanting to add something. Okay, and so back to what we were saying, we have an open position, and that is the education chair for our officers. Education chair, part of that would be getting all of the education programs. We meet every other month, 6 meetings a year, and your responsibilities would be aligning up the presenters for each one of those meetings. And you'd be working closely with our presidents and vice presidents, myself, secretary, our treasurer in education, and our membership chair as part of our officer board. And as well as we also have a board of directors. And so if you're interested and you'd like to be a part of us, and please, by all means, my email address is on our website, SoCal Chapter Iaei. Send me an email and I'll bring this up to the board, and we'll get a vote and get you on in there. Okay, thank you very much. And again, we thank you for tuning in to us today. And with all that said, I'm going to turn you over into the hands of our current education chair, Mr. Jared Walton.
Thanks for that, Daryl. So thank you everyone for joining us here today. I am your current education chair. I'm with Eaton Corporation. I'm an electrical engineer, focusing on applications of electrical distribution equipment. I'm going to be co-presenting today with Keith Johnson from Squared E Snyder Electric. And we're going to be covering a topic here that has been an amendment to the code a few years ago, but is something that we're still seeing the inspectors have questions about. 240.67 is a very recent change. We're going to be going through what to look for in the field, what do these changes mean, why is the code going through it, and kind of discussing these topics. Keith is going to be taking over the first half of our presentation, then I'll be finishing this up. Keith, do you want to get started?
Yep, let's get started. So we identified these two code articles, 240.87, 240.67, and we'll be concentrating on them. And they do not have any amendments, so they are an equal article reference and equal wording for the 2019 California Electric Code. Let's get started. I don't seem to be operating the arc flash incident. Well, I'll speak to this slide, even though we didn't have the action. There was a slide here that actually a video, short clip video of an arc flash incident, and probably from a lab experiment or test. But arc flash is the lights, heat, sound, and gases produced as a result of a rapid release of energy due to an arcing fault sustained by the establishment of a highly conductive plasma. So we all know, going back 20 years ago, most of our PPE, most of our safety precautions in the electrical industry were designed around shock hazard and avoiding shocks. But in the last 20 years, there's a considerable amount of study and testing and analysis and publications regarding the dangers of an arc flash incident. Once you draw an arc in typically in open air, that air becomes ionized as the arc continues. Ionized gases are highly conductive as compared with regular air. And as you eat away or as you erode the conductor, now you have airborne particles of copper or aluminum. And of course, those are also very conductive. And so you have this continuation of an arc fault being sustained. And that's why we refer to it as a plasma, because you have these gases, you have the tremendous amount of heat that of course is very dangerous, as well as a splattering of who knows what coming off of the conductor that's being consumed. So having recognized that, the writers of code articles have established certain requirements in certain applications for reduction of arc flash and arc flash hazards. Jared, if you could, there you go. So it's not just a matter of reducing arc flash. We'll look at a total system approach in this slide. We want to reduce the overall arc flash risk, and that means not only reducing the arc flash energy itself, but we want to reduce the likelihood of the arc flash from occurring in the first place, and ultimately the severity of that arc flash as measured in the heat given off by the arcing incident. We want to label the equipment, make sure all personnel are well aware of what kind of PPE is required. Currently, the code does not require us to label PPE protection, but we're headed in that direction. There's certainly some fine print notes that refer to publications that will allow you to come up with a calculation and a recommended PPE. Trained personnel, I mean, this can't be emphasized enough that the safety aspect is certainly one that is important, not only initial training, but ongoing training to remind people of the safety precautions. Reducing available fault current, this probably lies to the consulting engineer, the design engineer of record. Once the equipment is established, once the utility has set their transformer, the available fault current at each piece of equipment is pretty much set until there's a change to the electrical distribution system. But by looking at isolation transformers, moving equipment further away from the service entrance point, these are all possibilities during the design phase. Redirecting the blast energy, there is an ANSI standard for arc resistant switchgear. Speaks directly to the ability of an operator standing in front of the equipment to be safe if all the doors and covers are buttoned up and there's an internal arcing incident inside the equipment. The arc resistant switchgear will basically redirect the arc flash energy as well as heat and gases and smoke to different areas of the facility or outside the equipment where an operator is not likely to be standing. Faster clearing time is what we'll be directed, or what we'll be talking about mostly today. These are the solutions that are have taken hold in the industry, and we're moving in the direction of doing even more to keep this equipment safe, people safe. Move people further away. Obviously, there is NFPA publications that will allow us to calculate exactly how far people should be away from the equipment based on their PPE and based on their qualifications. And then minimize the probability of faults occurring in the first place. And this is ongoing with your maintenance departments, with testing and operating the equipment safely, safe operating procedures. Number one and first important is de-energize the equipment and lock out the circuits prior to working on equipment. I mean, obviously that's the goal. We can't always do that. Customers and owners don't always like that. But in those situations where we do have to work on equipment energized, that's the purpose for these code requirements. Most of the technologies we'll be discussing involve either redirecting the blast energy or providing a faster clearing time. So here's the first code article, 240.87. This has been in the code language for a few cycles now. You can see the grayed or shadowed text indicates where the code has changed from the NEC 2014 to 2017. So I'll go into this in a little bit more detail in the next couple slides, but just to highlight the changes, there have been two additional options for reducing clearing time and therefore reducing arc flash energy, number 5 and number 6. We'll talk about those and describe those. And then we've added even more informational notes as reference. So looking at the first part of the code, number 1, it talks about documentation. Documentation must be available to those that design, install, operate, and inspect the installation. So there are specific instances for this in this code wording where 1200 amps, where the circuit breaker can be rated or can be adjusted to trip at 1200 amps. This is a long time tripping setting of the breaker. This is anywhere in the system where these devices, these circuit breakers are installed. This code applies. And designers need to know where those breakers are if they're doing add-ons or upgrades to the facility. Obviously, maintenance personnel, contracted workers, contractors, journeyman electrician, all need to know where there is an option to adjust a breaker or enable these arc reduction methods before they do work on equipment energized. So documentation is important. And then we get into the reduced clearing time methods for arc reduction. There is zone selective interlocking, differential relaying, energy reduction maintenance switching with a local status indicator, energy reducing active arc flash mitigation systems, then the 2 new systems, instantaneous trip setting that is less than the available arcing current, and instantaneous override of the breaker, which is less than the available arcing current. And approved equivalent means, these technologies, I know I as a manufacturer, we see our companies working on new technologies all the time for arc reduction. So kind of a catch-all bullet point in the slide here, as well as in the code wording, allows for these technologies to evolve and be accepted in between the 3-year code cycle. Informational notes, there's quite a few. I mean, almost as much wording in the informational notes as there is in the code requirements. Most of these refer to documentations for safety in the electrical industry, NFPA 70E specifically, the latest edition 2012. Talks about workplace safety and procedures for following and determining proper PPE. And the IEEE reference there, 1584, the 2002 version, primarily deals with how to calculate the available arc flash energy based on a number of different inputs from the system. Available fault current obviously being one, but also the speed with which the equipment, the fuse or the breaker operates is critical to minimizing arc flash hazards and energy. Okay, let's take a look at the zone selective interlocking. You know what? I'm going to go back. I may have skipped a slide here. Yeah, let's look at these 2 slides first. When we talk about arc flash energy and arcing current, we're not talking about bolted faults. If someone shuts down equipment, maintains it, and then reconnects a wire or a bus bar to the wrong phase, maybe a dead short phase to phase or a phase to ground, as long as that's a bolted connection, that's not what we're talking about here. There won't be any gases in the air or explosions. This would be a dead short, which means we have low impedance in the current path, the fault current path, which means our devices will operate quite quickly. These are dangerous faults, but if our equipment is properly rated to handle the available fault, there should be no minimal danger to the operator. It's the arcing faults where we have a poor electrical connection between conductors or between conductor and ground that results in arcing current. And typically this expands into what we call the plasma, or the arcing current through the air, through ionized gases. And if you look at this curve, so we have on the left the I squared T, or basically the heating effect of arcing current. And on the right side, or sorry, the x-axis, we have the time in milliseconds that it would take for this energy to develop and then increase. And for about the first 100 to 200 milliseconds, it's pretty linear, kind of a low incline, if you will. And as long as we can operate and clear an arcing fault in 100 milliseconds or less, should have minimal damage. Obviously, we still want to suit up properly. We still want to do all our due diligence to calculate what that arc flash energy is. But the goal of all of these systems that we'll be talking about is to interrupt arcing current, detect and interrupt arcing current in 100 milliseconds or less. Between 100 milliseconds and 500 milliseconds, up to half a second, this is where personnel and equipment can be at major risk. So you can see we're only talking about a few fractions of a second or a few hundred milliseconds where we can go from being relatively safe with reasonably convenient PPE to being very dangerous territory. So it's all about the time and the speed with which we detect and operate our overcurrent devices. And if we let it go beyond a half a second, obviously there's even more extensive damage. Okay, so let's look at the first option the code lists in this code article. Zone selective interlocking. Zone selective interlocking is a way in which circuit breakers communicate to each other, primarily a main breaker or an upstream source side breaker and downstream branch breakers. you can see in this typical single line of maybe a switchboard that if we have a fault, let's look first at the incident where we have a fault on the load side of the B breakers or the branch breakers. If we have a fault on the load side of the branch breakers and we properly have set these breakers for selective coordination, either of the B breakers should operate first, depending on which one has the fault. Jared, give me a quick check. Someone is saying they don't see the presentation.
Yeah, can you guys let me look here at the participants. If anyone can hop off mute real quick and just let me know if you're able to see this. I know that myself and Keith are able to see it.
I don't see it. This is Izzy.
Sure, this is Prabhu. I can't see it.
Interesting. So do you guys have anything on your screen or nothing there?
Yeah, we have the zone selection interlocking, the ZSI.
Okay. So some see it. That's the slide I'm on, zone selective interlocking.
I don't see anything. I got a black screen.
I'm a few slides behind that, I think.
So it may have locked. If you look at the top there, it should say return to presenter slide at the very top. Let me see what I can do here to solve that for you guys. On slide 10.
Okay, I got video now.
Okay. So Keith, I'm just going to forward you on to slide 10 again. There you go. So you can take back control there.
Looks good.
Okay, great.
Okay, so let's look at if we have a typical downstream fault. Most of our faults, especially ground faults, occur way downstream at the end use equipment. So if we have a fault on the load side of B, either of the B breakers, those breakers should operate first to interrupt that fault and leave A closed so that we can at least power up the rest of the facility while someone goes to investigate, solves the problem before they reset the trip breaker. But what happens if we have a fault noted by the X there on the single line? What if we have a fault on the bus bar between circuits A and B? The A breaker has been set to delay in order to allow the B breakers to trip on a fault current first. But if we have a fault on the main bus where X is shown, we really want that breaker to operate quickly. We don't want it to wait because we know B breakers will not see that fault current. So what this zone interlocking feature does, it allows the breakers to communicate, and basically the B breaker will not send a restraining signal to the A breaker. The A breaker then knows that that fault is between the A and B, and it needs to operate as quick as possible. So even though the A breaker may be set to delay on a fault current, it will intentionally operate as quick as it can when it doesn't see a restraining signal from B. So this has to use electronic trip circuit breakers, and there has to be interwiring between those breaker trip units. Depending on the manufacturer, the clearing time is typically 700 to 100 milliseconds. So we're kind of right in the sweet spot of where we talked about we needed to clear these arcing faults to reduce arc flash energy. Costs can be moderate to high. If these breakers would normally be thermomagnetic, now they have to be solid state. That's one price adder. They do have to be a higher end trip unit for most manufacturers because they have to have a ZSI function, zone selective interlock function. And then there's a little bit of factory wiring labor to wire the controls between the trip units. The good thing is it's always active. You will not see a switch from the outside of the equipment. You will not see a switch that engages or disengages this function. It will always be there and always be active. The zone of protection is from basically the load side of the main to the line side of the branches. So we're mainly reducing arc flash energy should there be arcing fault on the main bus. The downstream from the B breakers really is not affected or reduced by this system. And then there's no visible indication. So if you're looking at it from a plan checker standpoint, you may see a simple note in the drawing of the single line to indicate which breakers need to have this zone selective feature. From a field inspector standpoint, you will not see anything different from a normal switchboard other than the breakers will need to be solid state. Now you can look up the catalog number of those breakers and verify whether or not the trip feature includes zone selective interlocking. However, it doesn't ensure, just because each trip unit has zone selective interlocking or ZSI, it doesn't ensure that the control wire has been put in place. So additional removal of covers to see those interlocking control wires is really what's required by a field inspector to verify this. Any questions on this system?
Keith, you don't have to have a slide that actually shows those connections, do you?
I don't, not on this particular one.
Okay.
I mean, as a manufacturer, I obviously have instructions that I can send you. So, you can shoot me an email, or I can take your email, or we can discuss offline if you need to see some more pictures or visuals.
All right, thank you, Keith.
So Keith, Mustafa, LA County. How you doing? So as
Good.
far as the selective interlock zoning only happens between A and B, what about the branch breakers down below on those panels?
Yeah, there's no improvement to or reduction in the arc flash energy for downstream faults using this system.
Mm-hmm.
Yeah, it only reduces the arc energy at the board itself, and only if the fault is on the bus or on the conductors between A and B, between mains and branches.
So the inspector is going to be verifying these at the site? Is that something that is going to be happening between the design or whoever designs the job? You said he just have to cover a note saying that it would be a zone selective interlocking?
Well, if I put myself in place of a plan checker,
Mm-hmm.
I'm going to need something on the notes, footnotes, keynotes on the single line to identify which breakers are going to have zone selective interlocking. And I have to make sure that those are both the main and the branches. You can't simply put this, for example, if A breaker is 1200 amps and the B breakers are less than 1200, you can't just put the requirement for zone interlocking on the breaker A, because it's not talking to anything. It needs to talk to the breakers that are immediately downstream. So that would be one thing a plan checker can look at, is to make sure it's properly called out for in the drawing notes, primarily on the single line. And the breakers that need the zone interlocking have to be identified. As far as a field inspector, if you want to verify as a field inspector that this is in place, reading the catalog number of the breaker and then having to look up that catalog number to verify zone selective interlocking is the first step. Second step is to look behind the covers and see the control wires from trip unit to trip unit.
I have a quick question. So say a board comes out, there's a pre-installed wiring harness with terminations that should show up on the shop drawings that come out with the board, right?
Yeah, if shop drawings are available to you, we as manufacturers do put in a detailed wiring connection diagram for this system.
Okay.
Yep.
So one more question regarding if A and B, if B is feeding another distribution board, not a branch.
Yep.
Does the selective interlocking will go beyond that as well, or would stop at B? Or does it go to C if the C is another distribution board?
So it can, but it's not code required. In other words, if B breakers, branch breakers are all less than 1200 and there's no code requirement for them to have zone selective interlocking for the downstream, for the next layer downstream, then there's nothing you can really require, and it's there is a benefit to it, and you could continue to have zone selective interlocking trip units downstream from these branches and factory wiring between them, but there is a limitation to the length of wire. If that panel board is 200 feet away, the next level, you're not likely to be able to make a zone selective interlock work between the branch breakers here B and the downstream panel.
So as far
Keith,
as designers, they will reach out to you guys, and you guys will, as far as manufacturers, will come up with this, or how does that work?
You know, it's a pretty standard option on a breaker, so there is no design aspect to it other than specifying the feature, the zone selective interlock feature. If they want, they can obviously get instruction manuals from us. We can give them a typical interconnection diagram of those control wires, but in fact, it's a factory installed wiring. So just like you don't expect to see an engineer give you a detailed ground fault wiring diagram where it's code required to have a ground fault, the designer is probably just going to call out for this feature, and it will be factory installed and wired.
And Keith, as far as the price, you said is more, or what are we looking at percentage wise?
Well, if I start with the thermomagnetic breaker, now I've got an add to go to solid state. So I'm going to say that's 20 to 25%. Could be as much as 30% for the bigger breakers, for the smaller breakers. And then another add for ZSI. So that's a higher end trip unit plus the inner wiring. So you could be looking at a good 50% add to a thermomagnetic breaker. Now, let's say this customer, this design engineer, is already going to specify the high-end trip unit because he wants it to be metering and communicating. Then it's already going to have the ZSI function, and you just need to pay the factory to wire. In that case, you may be looking at 10% add. So it's a hard question to answer, but those are the ranges. I'd say 10% to 50%, depending on what our starting point is.
Hey, Keith, we have a question from the chat.
Yep.
Trinidad's asking, can these breakers replace older breakers, or are they only used for new systems?
If you stay with the same manufacturer, and if the manufacturer has continued to build that breaker frame in the same physical dimensions, and if you obviously meet the requirements of current and fault interrupting, yes, some manufacturers' breakers can directly replace an older breaker with this zone selective function. All of us manufacturers, I think, have evolved our trip units in the last, I'm going to say 5 to 7 years. So the window is closing on being able to replace anything older than maybe 8 years with a new updated trip unit. Some manufacturers obsolete older designs 5 years after they take it off the market, and others will continue to manufacture them for years. So, another good question, but another tough one to answer across the board. All right, differential relaying. So take a look at the single line. These happen to be draw out breakers, but this system can be used with fixed mounted breakers as well. There's a electrical law called Kirchhoff's law that says at any point in time, if you measure the incoming power to a circuit and the outgoing power, it should be equal. So in this case, we have incoming source of power going into the main, and we have 3 branch breakers with outgoing power to all 3. So if I take current transformers and I capture the amount of energy, the amount of current flowing in and out of this main board, at any point in time, the amount coming in and the amount going out should be equal. If it isn't, that means there's stray current going somewhere, probably phase to ground. And if we put a relay to accept the inputs from these CTs and do this comparison electronically, we can detect and operate the relay such that it trips the main, put a shunt trip function on the main breaker, and we can clear any potential arcing fault. A little bit slower, you can see in the notes, we're doing 150 milliseconds instead of our preferred 100 milliseconds and less. But that's the basic concept of this type of protection. The good thing is it's always active, just like the prior one we talked about, ZSI. You don't have to turn this on and off. It'll always be on and active as long as there's current flowing. Our zone of protection, we expanded a little bit. So in this case, we're showing CTs on the line side of the main and on the load side of the branches. So now our zone of protection is between the CTs, so we included the main and branch breakers in this zone. We're showing fairly expensive costs, so I'll explain that. Differential relay protection requires very high accuracy CTs. So these current transformers, a lot of laminated core steel, a lot of windings, very big. The size will prevent us from group mounting those branches, so we might have to individually mount the branches. And in doing so, we might have to have more sections in a switchboard than we normally have. So the combination of the additional components, expensive components, and the size of the equipment all contribute to this greatly increased cost. Now you'd think, hey, if I'm going to spend this much money, why am I only getting 150 milliseconds? Why aren't I quicker? Well, number one, it's the time to detect this differential. It's the time for the relay to react and send the the trip circuit signal to the main. And then, of course, you have the clearing time of the main breaker itself. This similar type of CTs with a relay is what a plan checker would see if this type of system was being called for on plans. And as far as in the field, this 87B bus differential relay is typically mounted right on the door or cover near the main breaker. So this one's easier to detect than the last one we talked about as far as field inspector looking at it. The 87B number is an ANSI assigned number. ANSI has a whole list of relays and types of protection, and they happen to assign differential protection with 87, and the B stands for the bus protection. If you see an 87T out in the field, that means it's protecting a transformer. Any questions on this one? Yeah, I'm sorry about the buffering and some of the freezing slides. I'm going to go ahead and continue and hope that in the background, Jared can handle the questions. All right, let's move on. So now we look at the most popular one that we've been seeing, and I'm going to skip down to the bullet point that says cost equals dollars, and that's the main reason you're seeing this as the prevailing method to meet the code requirements. It is a lower cost solution, and it takes up less space. So earlier question in our officer meeting today was, what do we call these? How come there's so many acronyms and different names for these? There isn't any code defined acronym or terminology. Maybe a couple code cycles from now, if someone introduces a change to the code to actually identify these to make it more uniform for a field inspector, it would be nice. But currently, the most popular, I think, are energy reduction maintenance switch, ERMS, or arc reduction maintenance switch, ARMS. Within my company, we also have MMS, which is just maintenance mode switch. All these are different acronyms or abbreviations for the maintenance mode switching that we're going to talk about here. What basically happens is we have a circuit breaker, and it has to be a solid state circuit breaker, and it has adjustments on it. One of the adjustments that applies to arc reduction of arc flash energy is the instantaneous setting. Typically on a breaker, the instantaneous settings can be adjusted from 5 times to 10 times the trip rating of the breaker. So if it's a 100 amp breaker, you can adjust your instantaneous or your arcing current or fault current tripping feature, if you will, from 500 amps to 1,000 amps. Some solid state breakers will adjust lower. Some solid state breakers have the ability, using an external input, to trip much quicker than and at lower amperages. So in this case, we're looking at a selector switch, which is external to the breaker. It's typically going to be a 2-position. It'll just be an engage or disengage of the maintenance mode. Sometimes it's on and off. Most manufacturers identify this with either a blue indicating light, or sometimes the handle of the switch itself will be illuminated and glow in blue. So that seems to be the industry, where the industry's headed. So far, there's no code requirement that it has to be blue, at least not in the 2017 NEC 2019 California code. The components for an external switch would be obviously the selector indicating light or illuminated selector, the electronic trip unit on the breaker itself, fuse block and power supply to power the indicating light, and a clearing time achieved of 50 milliseconds, pretty quick. Now, this is only active when the arms or the ERM switch is engaged. And so this would be maybe one concern for an operator, is you got to remember to engage it. Most manufacturers, when they have an external switch like this, will provide the operator with a padlockable attachment so it can be locked in the engaged position when someone's doing energized maintenance. I'm going to go to the next slide before I ask for questions, open it up for questions. So this particular device, what we call our EZM, is the wall-mounted multi-metering, residential metering type equipment. And you can see this type of equipment is typically in an enclosure that's both indoor and outdoor rated. So we're not always going to have a nice cover like this over the engage and disengage switch or the maintenance switch, but it happens to be on this equipment. We have to make it weatherproof. So that's why you have such a cover. So it sits next to the main breaker. I have the inner wiring, any kind of interface relay, and obviously connected back into the trip unit. Any questions on what you're typically seeing out there today? This maintenance mode switching. Here's another picture. This is now a switchboard, not the wall-mounted multi-metering main. So in a more traditional stand-up switchboard, we also have an external selector switch, some relaying, and necessary control power to operate that indicating light. By the way, the control power is not needed to operate the energy reduction maintenance mode. That's all self-power based on the breaker itself. It's only the indicating light that needs that extra power. All right, now we talked about in the previous slides an external operating switch, maintenance mode switch. There are manufacturers who build these switches and indicating lights directly onto their trip unit. And in this case, this is a Eaton Power Expert Release PXR trip unit. You can see the arms, what Eaton calls their arms switch. It just says on, off, remote. So there's a little indicating or slide switch. And then a maintenance mode light, a little rectangular light there next to it. We talked earlier about how hard it is on the original or the first option to identify ZSI. In this particular breaker, you can see a ZSI is written right on the face of the breaker. So if Jared, you want to take over and add any additional comments to this slide and then go on from there, and I'll be looking at chat.
Sounds great. Thanks, Keith. We actually just had a chat question come in here from Wes, asking about the ERM settings preset in the trip unit, or does the contractor set them?
Now, so, yeah, and this is going to be particular to each manufacturer, and even within each manufacturer, there is going to be different options depending on the size of the breaker. The smaller frame breakers, which we probably will not see much of because they're not code required until we hit 1200 amps adjustable breaker. But the smaller breakers may not have multiple settings within the ERMS. They're probably just going to have one factory preset. So there's nothing to worry about for smaller, I'm going to say 400 amp frame and smaller. 800 amp frame, maybe 600 amp frame if a manufacturer has such a size, and larger. There will be options to actually adjust when the ERMS trips. The reason for that is we do have, under normal conditions, we do have some circuits that do have inrush currents, and we don't want the breaker to nuisance trip. Even though we're doing energized maintenance of that circuit, we don't want the breaker to nuisance trip when we have a large motor start, for example, or we're energizing a downstream transformer. So a good coordination study will identify where those inrush currents are, and we'll have a recommendation to set the ERMS or the ARMS just above those inrush values that we know are good, and below those that we know will be considered an arcing flash or a fault current. As far as who determines when those are set, the engineer of record should identify where those should be set. I know from my standpoint, most contractors would go back to the engineer of record and say, hey, this thing has an adjustable ERMS. Where do you want me to set it? Just like today for ground faults, GFI systems for the service entrance ground fault. As a manufacturer, we ship those out on minimum. And a good contractor would go to the engineer of record and say, I don't want to leave this on minimum. If that's not what's good for the owner, what do you want me to set these? So I think it falls on the engineer of record as far as an inspector and plan check. Certainly not a requirement of plan check because you don't even know which manufacturer is going to land the job to know who's breaker. But once it hits the field, there should be an engineer of record who's involved in determining where that should be set. And the contractor can set it, or another independent third-party testing company. And that will all be dependent upon how the owner set up his specifications on the equipment.
So Keith, Mustafa, can you go back to previous slideshow there? Yeah. So now go forward. Yeah. There's one more. Go forward one more time. Yep. There we go. Okay. So somehow, somewhere, the installer realized that either the engineer didn't specify this, or the installer wants to use this instead of the others, the method.
Right.
Can this be added on to any breaker?
Any breaker? No. It will have to be a breaker that has the electronic trip unit, number one. And number two, the higher end electronic trip units, which have the zone selective, the ERMS or ARMS feature. So not every solid state breaker has the ability to simply add a switch in the field and away you go. There are particular trip unit models that have this function and others that do not. Certainly a thermomagnetic breaker without a solid state trip, I'm not aware of anyone in the industry that can do arc reduction with a thermomagnetic breaker.
So as I can see on that picture,
yeah,
that has got mounted on the bus. So can somebody could do this after the gear is at the site?
Well, you're talking about the components on the right side of the breaker?
Right, exactly.
Well, if you look, there's a little gray mounting pan that they're all mounted on.
Mm-hmm.
So it may be an illusion that this equipment is mounted on the bus, but yes, we as a manufacturer have caught, and we're going back a couple code cycles when this arc reduction was first required. There were a lot of missed applications, and so our field service group went out and added this equipment, maybe even changed out the breaker so that it's compatible. But yes, we consider this field installable or field retrofittable. I think Rich Berman may be on the call,
Yeah.
but
I was gonna call him out. Yeah.
so would adding this in the field represent
Sure, go ahead.
a modification? Changing out the breaker wouldn't if you could stay within the same frame size. There would be obviously for this particular one, there would be a change to the front cover so we can allow the switch to protrude through. Is adding ground fault to a switch, an external ground fault relay, considered a modification? Unfortunately, no clear code states that, especially for the arms and the ERMs. From UL standpoint, once you modify the equipment, particularly the busing, which would not have to be modified, then you are looking at a recommendation for field evaluation. Go ahead, Rich.
No, you're right. And if the equipment is covered as a field installable in the file, then there should be no problem adding that in. It would be in accordance with the instructions and markings.
Just speaking for myself, for my company, Square D Schneider Electric, our instructions are geared for field addition or field modification to add this feature in the field. So from my standpoint, the only thing you're pretty much going to add is that mounting bracket and a modified cover to allow that switch to poke through.
So that would
Right.
Jared. So Jared, what about Eaton?
So all of our trip units have the capability to not even have the switch. So if you have like a power circuit breaker like that and you wanted to change it out, you would be changing out the breaker itself. So some of those controls would already be there, but if you wanted a light, you'd be doing the same modification. This slide here shows what it looks like on a molded case breaker, which is really at 1200 amp. Most of the times we see this come up is at that 1200 amp level, where clients they missed it for some reason. So it's going to look similar to this. There's going to be a little on-off switch on the front of the breaker there. If you see the arms on the upper left, and that's going to light that little blue light, or there's going to be a little dial that they turn with a screwdriver in order to activate that ERMS setting. So it can easily be swapped in the field.
Thank you.
Great. Okay, so I'm showing here our new Power Expert breaker. You're going to see this more and more as an industry standard. It's the kind of the dichotomy. We tell people to get away from the equipment in order to get outside of the arc flash boundary, and then most manufacturers are starting to add LCD screens that everyone wants to come look at. So it's kind of just a little dichotomy there, but with new things like this, we're powering these breaker trip units separately. So you can turn off the breaker, de-energize the board, and walk up and see the device there. Oh, looks like my presentation just dropped. Let me toss this back up here.
Sorry, Jared, I stopped presenting, so apparently
it's all good. So going through, so when we talked about these type of ERMS, ARMS, active reduction maintenance technology, we're talking about changing the way the breaker senses itself, right? The thing once Keith talked about previously, we talk about ZSI, we're talking about breakers working together. Here we're talking about breakers working independently. The next side of this is looking at a more complex system. As we talk about with these type of systems, the only real control we have to reduce arc flash energy is reducing the time it takes to clear that arc. Inside of the breakers themselves, we don't really realize it, but there's two separate times. One of those times is the sensing that, hey, a fault has occurred, right? There's a short circuit, there's an arc event, and then the actual opening time of the device. So these more complex systems are now separating those two characteristics into two different portions. So what we're using now is specialty sensors called photosensors and relays to do the logic for the breakers. Now, instead of just looking for rises in current, we're looking for that along with light being produced from when we have one of these arc events. So it's that energized gas that Keith talked about. So we're using photosensors, current sensors, and then these separate relays, like right here, this VAMP 321 unit, that is going to tell the breakers to shunt trip. So the breaker's not making that logic deduction, but these separate units are. Now, this is where the code opens it up a little bit, because this system is really dependent upon the manufacturer and the type of system that you're using. So typically these things they can be field installed. They can also be factory installed. The clearing time here, even though we've added these additional sensors, it's going to be about 87 milliseconds. So there is this additional, even though we can sense that an arc event's happening, we still have some processing time in that unit. And the long leg on this stool, if you will, is going to be the actual breaker opening. That mechanical process of the device opening, creating that arc between the two plates inside the breaker, all of that takes time. And then for the breaker to go, the current to go through a zero cycle so that it will actually stop. So what we're doing here is the breakers aren't necessarily smart, but we're adding a smart system and shunt tripping those devices. This is obviously a very costly system. And this is something that, as you're looking at from a plan check or from a field perspective, the engineer, the end client's going to be telling you, we have this system in place. Because for many clients, this offers them much greater control than just meeting the 240.87. It gives them a much wider range of, it's a much better solution. So I'm going to go through one type of this system. This is one that Eaton makes, and this is called an arc quenching system. The one thing unique about this system is instead of waiting for the breaker to open, we're adding a secondary device, which is going to actuate before the breaker. So this additional data that we're receiving from the photosensors and this arc flash relay, we're going to be able to act on it a lot quicker than in most systems. So the way this works is we have a CT at the load side of that breaker, and we have a photosensor inside each cubicle, inside the terminal compartment, and inside the cross bus. Both of those pieces of data feed over to this relay. And when it sees a rise in current with a light flash event, it knows that it needs to trip. There's programming built in there where it communicates with the breakers so that it's aware that if the breaker's opening as normal, that the unit is not going to accidentally trip when the breaker's just clearing a normal fault. Once it senses this, it sends two signals at the same time. One signal is going to go to this little blue box down here. If you notice, it's the same size as the breaker above it because it's doing something similar. It's a switching device. And it's also going to send a signal to this main breaker. The way this technology works is that the main breaker is actually still clearing the fault, as in any of the systems we've discussed previously to this. But now we have something that's riding through. This quenching device essentially eats the arc. So wherever the arc is happening inside of the system, it creates a lower impedance fault inside of itself. So it's a sacrificial one-time use unit that allows us to stop the arc in around 4 milliseconds. So when we look at that curve that Keith presented at the very beginning, we're stopping the arc before it propagates, before it starts extruding lots of this vaporized gas, before the pressure wave, which causes the big ball of electrolyzed flaming material that comes out at an arc event. So we're stopping all of that because it's actuating so quickly, and the cost of that is one of these devices. So it's taking all of that damage internally. That unit holds in until the upstream breaker clears the fault so that there's no current flowing and the propagation is finished. So here's what's actually inside of that device. In order to actuate within 4 milliseconds, it's impossible to have an actual breaker with mechanical contacts open, or even a vacuum breaker. So what we use is something similar to our vacuum bottle technology. It's not a vacuum, but we use a small little piece of copper, a little filament here that resides between the two plates. Now, when this unit, the arc flash relay says, hey, we're having an arc event, it sends a little bit of current through there in order to cause that ribbon to connect these plates. Now, if you notice, what we're doing is creating a fault between A, B, and C. So we're creating a fault here, and the lower impedance is due to this small little ribbon here. The key of this technology is, instead of doing a bolted fault, as we talked about in the beginning, where all of the phases are connected, which amounts to a huge amount of inrush into the equipment and can cause a lot of mechanical torsion and stress, we're creating an arcing fault. So we're roughly 38% of that in order to contain the arc in this type of situation. Now, because the unit acts so quickly, and like I said, there's no ball of gas or anything else, this actually is equivalent to meeting arc resistant standards. Arc resistant standards for this type of equipment says that if you have a piece of cloth within 2 inches of the front of the device, that the cloth is not going to burn up. This technology actuates so quickly that it meets that standard. It's tested and it passes for that type of protection. This is, again, something for plan check. Your client is going to know that they're going to be using the system far ahead of time. And they're going to want to do that because, unlike an ARM system, which is very fast but has to be manually activated, the system is on all the time. Right now, one of the disadvantages of this type of equipment, though, is it's only available in switch gear. So there's no switchboards or MCCs. It has to be UL 1558 low voltage switch gear. Any questions on these software kind of energy management systems in lieu of just a single device?
So, Jed, Mustafa, so we inspect this switchgear and switchboard, and they have all these arc flash reduction devices today. 5 years from now, the electrician wants to go in there and one of those breakers gone bad. How, as inspector, how we know that he is replacing those breakers properly? Because there is no marking. The code doesn't require any marking. That gear doesn't get marked with anything.
That's a great point. So when we look back at the individual breakers with like that ARMS and ERMS system, that breaker itself is its own contained unit. It doesn't have any logic outside of it. So if they're replacing a legacy breaker, like you said, in 10 years from now, with a new breaker, they just need to make sure that breaker itself has those characteristics built into it. The only wiring and control might be if the client wants one of those little blue lights or something like that to know when they've actuated the system.
I understand what you're saying, but as far as the inspector looking at a gear that was or a breaker has been replaced 5 years from now, how do we know? There is no marking, there is no indication, there is nothing that is going to help us, in a couple of years or a year from now.
Yeah, this is Keith. So I think because of the newness of this technology and the fact that the code does not stipulate how much of a reduction in arc flash energy has to occur, how quickly the device has to operate. There's so many technologies out there. We really haven't, as an industry, started to focus in or narrow down all the different options, and whether or not that's going to take updated code cycles to more clearly define what qualifies, what doesn't. I'll maybe call on Rich again if he's still listening. Is there anything on UL side that is now actively looking at qualifying or testing the arc flash reduction methods so that there's going to be eventually an easy certification or a mark on the equipment that you could go to UL or one of the other testing agencies and get a sign off for a certification?
Keith, I'm not aware of anything ongoing right now, and it's possible there may be, but I just don't know anything about it if there is.
Yep. Sorry, Mustafa. And there's no easy way to identify these. And like you said, especially replacement 10 years from now, there hopefully will be a standard by then, or an easier way for a field inspector to make sure it qualifies as truly protecting the operator, but not at this point.
Yeah, no problem. As a poor inspectors, they rely so much on us, and I don't know how many inspectors have been actually trained on this, and are going to be looking for this as well. And how many installers have been, trained on this, and as well as the consultant engineers.
Yeah, well, Jared and I work directly with consultants, so
I know you guys have a monthly. I know you have either monthly or bi-monthly meeting with the LA group.
Yeah. We could. We haven't started virtual ETAC yet, have we? So.
No, we're going to. We're going to.
Yeah, that would be good as a start.
Okay. So
but Jared and I
promise this would be the first item.
The most effective tool, I can guarantee you from my perspective, since Jared and I call on consultants, the most effective tool you have is your plan check correction comments. Because if you put on there, hey, must show this, or must have a nameplate that identifies the system for the field inspector, or, if you come up with requirements coming off that correction checklist, boy, the designers certainly react to those comments. They do not like to see those comments come back and have to resubmit plans.
You are right. Absolutely.
So, to your question, Mustafa, this has been in the code now since I believe the NEC 2015 cycle is when it was added. So we're starting now to finally see adoption in the field. But now that the technology is very prevalent, where contractors can get it from every manufacturer, there's easy solutions to meet this. We're trying to make sure everyone's aware of what's going on. So once in a while, I'll see people find it in the field. Like I said, Keith and I are trying to educate consultants on this because we need to make sure that the right stuff's getting out there first, along with making sure that you guys know what to look for. So, and then the third step of making sure clients actually know what to use, how to use what they bought to protect themselves.
Thank you. Great.
So there are three other methods here that we talk about, and they're a little different. So while the other ones are technology-based solutions, this is a calculation-based solution. So we talk about that arcing energy. Now, if the breaker has the ability where you can set the instantaneous below that available arcing current, that also meets the intent of this code. So essentially, if an arc happens, the breaker is going to trip instantaneously, meaning the fastest that it can with calculation. The reason why we don't see this as often is because when engineers are designing systems, they don't know what manufacturer is going to get chosen. So they don't know they don't want to pay or do the work up front to do a study that's probably going to become invalid. So this tends to come up when you have a system that's been installed in the field. Let's say it was missed. They're saying, how can I meet this code intent? The answer is, well, have your engineer go back, look at the study, and see, can you coordinate your system so that 1200 amp breaker is set below your arcing current? And if you can do that, then it meets the intent of the code. That's what we're trying to achieve. In some systems, that's possible. In other systems, it's not. Because the arcing current, although we view this arc as this really dangerous thing, if it's a small little strip mall, the available fault current isn't high, so the available arcing current isn't very high. So that it might not trip the breaker instantaneously, which is why, again, this whole code issue got brought up. The second way to do this, and we see this more on breakers with higher end trip units, is that they have an instantaneous override value. So although the client and the engineer can decide to set the instantaneous back in order to make the system more coordinated, that there is an override. There's a line in the sand where that breaker is going to trip, no matter what the settings are, because that's been built into it. So if that instantaneous override value is again below the arcing current, it meets the intent of the code. So both of these things, like we say, it's hard for engineers to design it beforehand. There's no cost or technology here. This is just engineered with a study, but it is a solution. If you have a client in the field who has an issue like this is some of the solutions they're going to present to you. Instead of replacing the device, is working with whoever did the study to dial in values to make a safer system. The last one here is this is wonderfully vague approved equivalent means. So this is you as an AHJ working with a designer for some approved version meeting the intent of this code. Typically, that's going to be the last two that I presented, where they're doing settings, not technology based, but more engineering and calculated based solutions to this. Last slide here on this system, and then I'm going to talk about really briefly about what we have on the fused side of things. So for breakers, each of these technologies, like I said about that time where we're sensing and the time that we're actuating. So ZSI, as we talked about first, there's a lot of communication there. The main breaker has to talk to the feeder breakers and feed back in before it can decide how to react. So it's going to be the slowest. Software instantaneous trips are meaning that the breaker itself is calculating, hey, there's been a rise in current, the RMS, that root mean squared. It has to actually do that calculation. It's waiting for that to happen before it actuates. We get a little lower when we start doing arc detection relays. So now that relay is seeing a light sense and it's sending a signal to the breaker. Same thing with bus differential relays. We're doing these computations based off the external signal. We're losing current somewhere, tell the breaker to trip. But you notice when we get down here to the ARMS, ERMS systems, there's a dramatic decrease. Because when we're doing these, we're taking out a lot of the logic processes. And this breaker is now reacting as fast as it physically can. So at Eaton, we like to brand market it as faster than instantaneous, because an instantaneous trip is about 10 milliseconds here, where we're talking about, these are energy levels. So about 10 calories per centimeter squared for software instantaneous, and you're looking at about 6 for one of these arc reduction devices. The other reason why you're going to see, and we kind of want to do this presentation, is ARMS and ERMS as a value proposition is less expensive than everything above it to the right. Now, these offer different advantages to certain clients, like ZSI is very popular for hospitals because they can use it to coordinate a ground fault system. But when we're looking at the majority of clients who have a single main or a few devices over 1200 amps that don't really need to trip in a sequence other than their studied coordination curves, this ARMS and ERMS has become very popular. It's an easy button for engineers to use, so you're seeing it a lot in the field. The one caveat here also is this energy level looks really good. But again, this is a manually operated system. So if the blue light is not on, this level of protection is not actually being provided. It's going to be back up here with the software instantaneous. That blue light has to be switched. So we're seeing systems, and you'll probably start seeing it more in plan check, where clients are dialing in this ARM system and tying them all together. So they can do it outside of a room even. They'll walk up to the door, they'll hit a switch, and all of the devices in the room will now activate that mode. That way they don't forget to turn it off when they leave the room, and that way they can wear the PPE appropriate at a lower level because all of the devices have been actuated. So this is kind of the point here. Now, arc coaching switchgear is showing up there just to show where the industry is going with this new trends of other devices that can actuate before the breaker to take care of the fault while the main device opens. So I think it's the end of the breaker side of things. If anyone has any questions on this technology, I'll move over and kind of quickly touch on the fused side. Question here in the chat: is there any risk if ERMS is left active after the work is done? That's a great question. So the issue is the breaker and the system are going to work fine, but now you've lost coordination. When you use that ERMS switch or ARM switch, you're essentially having a second set of settings for that device. And we're going to the normal settings of everyday operation, and we've went down into this maintenance mode where the breaker is going to trip much quicker, but it's no longer necessarily coordinated with the rest of the system. There is a chance it can nuisance trip. So the engineer should have done a job to say that it's not going to trip on a motor start or something like that, but you don't want to leave it at that lowest setting. If you were able to leave it at that lowest setting, that should have been the settings from the engineer. So it's a coordination issue, not it's just going to be a nuisance trip issue versus a safety issue. So if that's it, I'm going to step over here to the fused systems. Now, this is the newest part of the code that was just adopted with NEC 2017, California Energy Code 2019. This is going to be a lot shorter because we're basically adding in everything we talked about previously. But for fused systems, there isn't as much as we can do. Obviously, because in a fused system, typically these fuses are manually operated instead of this ability that we're used to with the breakers where they can be sent signals to actuate via shunt trip or something else. So in the NEC now, it's talking about fuses, 1200 amps or higher. A and B shall be installed. Now, they do this not, I guess I would say infrequently, but this code said the requirement shall become effective January 1st, 2020. The reason why is they were giving a time for manufacturers to come up with solutions, because at the time this was written, there was not the ability to do this at fused systems. And even now, there's only 2 manufacturers who have solutions to this. Usually what we're seeing is we're just going to move clients over to breakers because it's going to be simpler than doing some of the arc reduction for fusing. So when does this come up? 1200 amp fuses. It does not matter the voltage. When looking at this from the NEC, there's this method B here. It's saying that the fuse must have a clearing time of 0.07 seconds or less. That's the clearing time of a breaker. So they're saying we want the fuses to clear as quickly as a breaker. And if you can't do that, then you need to look at one of these 4 systems. So obviously we just talked about this. You know about differential relaying, you know about the energy maintenance switch, and arc flash mitigation systems or approved equivalent means. They're all the same methods that we just talked about before. The thing where this comes up though is when this first was announced, I saw a lot of consultants confused because it says right there 0.07 seconds. Well, if you look at the full rated value of a system, say if it's 65K from the utility into a main switchboard, that fuse is going to burn up really quick. But the code here again is specifying arcing current instead of bolted fault current. That's going to require a little bit of extra diligence here on the part of the engineer to verify that they have the correct fault current if they want to use a fuse switch without adding any technology. Here's a nice little slide Keith put together. You can see here's the 0.07 seconds. And these are the various fuse curves. If you're not familiar with this, you can see this is the current in amps versus the time it takes for it to burn. So as the current goes up, the fuse is going to burn quicker. As the current goes down, it takes longer for that fuse to burn. Because of this, it gives us an idea, like right here at 10,000 amps, none of these fuses are going to burn up in the 0.7 seconds. So at 10,000 amps arcing current, even a 1200 amp fuse isn't going to actuate. The question is, all right, what's a good rule of thumb between arcing faults and bolted faults? So we put this kind of slide together here. So if you're working with a 208 system, and if the available fault current there at that device, so if it's not the main service incoming, the engineer needs to calculate what the available fault current is. They have less than 50K at that 1200 amp fuse, they need to have another technology involved. So for two-way systems, where we usually see fuse devices because they're value engineered instead of breakers for these systems, they need to have a very high fault current in order to meet that requirement of 0.07 seconds clearing time. 480 systems, it's a little bit easier to meet because there's going to be more energy flowing through. Now, if from a plan check perspective, if someone sees the switch over 1200 amps, they need to be asking this question. Can you show me, does it meet 240.67? That means the engineer needs to go get that calculated value and show what the minimum voltage fault current is and pull up a fuse curve and show that, yes, the fuse will actuate underneath this curve within 0.07 seconds. And if it can't do that, then we go look at the next four. Now, for these systems, for residential, light commercial, strip mall, those type of operations, fuse switches aren't typically actuated unless we're using a ground fault. Usually they're manual devices. So Eaton is releasing something this year where we're using our ground fault Pringle fuse switch and we're adding an arms to it. So on the left side, you see ground fault, like a normal ground fault fuse switch. And on the right is overcurrent, which allows settings to be dialed in for an arms protection so that so someone can go up, set an arms device, and that fuse switch will actually open before the fuse would burn. We're not really seeing the bus differential, those other relay technologies, and ZSI and things like that aren't really implemented because it's never been needed before. So the majority of the time, we're going to see clients move to a breaker setup from a fuse switch, unless they're using solar. And if they're using solar, they're generally going to have lower fault currents. And if they have a large switch, in order to meet the visible disconnect, they're going to have something like this. The other option out in the field is from our friends at ABB GE, which has a fused, instead of a fused switch with blades, it's using a similar thing to a breaker or a contactor above a fuse setup. So that way this unit can be triggered like a breaker to have a pickup, a release, and to open, or it can be set to held in and use the current limiting characteristics of the fuse. Kind of a best of both worlds mix here of a breaker and a fuse combo. This unit also does have a blue switch, similar to how a breaker would have, because there's an integrated trip unit inside of it. Now, Prabhu just posted something in here in the chat as well. He's our local rep for ABB GE about their RELT system. So it's similar to the ARMS or ERMS, the RELT, is it their blue light technology. So he just posted a nice little white paper there, his contact information, and a web link if you click on the conversation button at the top. Prabhu, is there anything you'd like to add?
Oh, no, I think you guys did a pretty good job. Thank you. And very similar to what Keith said it earlier, and similar to the ERMS and ARMS, you probably have to add one more acronym to your dictionary. It's called RELT. The system that you see on the screen, it stands for Reduced Energy Let Through. It's a similar system that Eaton's and Schneider Square uses it, except we actually taken the breaker technology that we implemented to the Power Break 2 into a fuse option that you see over there. So when it comes to the RELT switch integration, it's exactly the same system that we do to comply with the Article 240.87.
So that's everything that I had for today. Again, quick overview. 240.87 is for breakers. 240.67 is for switches. The big thing to remember here is anything over 1200 amps. So if it's over 1200 amps as a fuse or as a breaker, there needs to be something on the plan check documentation that says, hey, make sure you include this technology. And then it's on to the manufacturer and the contractor to make sure they have that. But your inspectors in the field should also be asking, what are you using? If it's 1200 amps, it doesn't matter where it's in the system. What type of technology is getting applied there?
Keith
All
and Jared, great job. You guys did awesome. That was very good. One more question from me. Would this arc energy reduction for fuse and breakers will help the arc flash hazard warning that we have to comply with under 11016?
So you're talking about the new requirement for the clearing time?
Well, 110.16 calls for arc flash warning. Okay, and that's specified. We have to provide all that.
Yeah.
Would this arc energy reduction for fuse and breakers will help the owner of the facilities or the installers or whoever is doing the arc flash study to get that study done properly?
So an arc flash study is not required by code, and the values determined by the study are not required to be posted on the equipment. The warning label is only that, just warning arc flash hazard. That's pretty much it. There is an addition this year's code that says the clearing time of the main device has to be identified on the board. And certainly if someone's going to do a study after the fact, if they can rely on that clearing time for the main, it will make their life much easier and quicker, perhaps, to come up with the arc flash energy number and therefore the PPE required. But in terms of doing a study and posting the study results as far as PPE or arc flash energy and calories per centimeter squared, that currently is not part of the requirement for labeling on the equipment. Code is gradually heading in that direction, but not so far.
Yeah. Thank you.
Hello, Keith.
Yeah, go ahead.
Quick question about the arc flash result. Let's say PP level and for clearing time and all the features of that label that being installed in the field on the switchboards. How long do you think that those results, if being installed, being valid? Like how many years?
All right. So the fine print notes I talked about early in the presentation refer to NFPA 70E, which is a good safety standard for an owner to use. It's not code required. It's not an enforceable document at this point. But in that document is a recommendation. I think the latest edition says for every 3 years is the minimum recommendation for someone to go back and revisit. Has anything changed in the system? Has the utility changed their transformer? Has the impedance changed between protective devices? And of course, it'll depend on the facility too. If you're talking about a warehouse, that thing almost never changes unless you expand it. If you're talking about healthcare industry, probably every 6 months they're adding a new piece of equipment or adding new patient beds or rearranging their loads. So hard question to answer, but depending on the facility, it may be every 3 years as the NFPA 70E recommends.
Yeah, I agree, because sometimes the let's say the available fault current from the utility company, that might change over time, and also inside the facility itself, sometimes they they add some big motor and then motor contribution changed. It just throw all the result after the you gotta be revisit the study again. So yes, I agree.
One thing to note here is when you have these technologies implemented and the client has done an arc flash study, they will actually have a label with two portions. One without the technology implemented, one with the label with the technology implemented. So it's another easy way in the field to look and see if this has actually been done.
All right, is that it, everybody?
I think that's it, John.
That's it. Well, once again, hey, Jared and Keith, thank you guys very much for putting this on. We really, really appreciate it. And we look forward to seeing everybody back on October, what did we say? I just lost my page on my notes. October 14th. No, sorry, guys. We're blocking October. It is November 18th. We'll see everybody back in November 18th. Thanks again, everybody.
Last thing, if you do want to have a CEUs on this, please send me an email. You should have my email from when the meeting announcement came out, but please send me an email if you'd like to get CEU credit for this.
Jared, is the presentation available?
Yes, it is. We can provide that.
Okay, on our website, or how would we get that?
Let me see if they can post it.
Okay,
if you would like a copy of it, send me a note and I can send it to you, but if not, I'll try to get it posted online.
Will do. Thank you.
Great,
Thanks, everybody. Have a good day.
Thanks, guys.
Excellent job. Thank you.
Thank you, guys.